Good afternoon, everyone. I'm Morris from TX1 Networks, and welcome to the section. In this section, we will talk about how we have come up with a new practical approach to apply symbolic execution to effectively detect the various malicious behavior and ransomware. The engine we provide later can overcome some of the current bottlenecks of static and dynamic analysis. And this is also what we think this is a new trend for the future blue team. And I'm Morris. I'm currently the manager of TS1 Product Security and Research. In the past, I often give speech at major cybersecurity conferences, including Red Hat Europe, DEFCON, RSA conference. But this is the first time with our team have shared on the Red Hat USA stage. We are very honored. And my colleague, Sun Hao, is a researcher of TX1 Networks in the present here, and also often spoke at many cybersecurity conferences, including Red Hat Arsenal, DEFCON, HICOM. He also focuses on Windows attack techniques and research. Also is the author of the best-selling book, Windows IPT Warfare in Taiwan. And last one is Hank. He's also a researcher at the TX1 Networks. He's a CTF player and focuses on the malware research and Windows security. And in today's online, we will start the newly sustained landscape and discuss the current limitation of static and dynamic detection. Next, we will share why we use symbolic execution, where our idea comes from, and what functions our engine provides. And finally, verify through real-world malware samples. And we will use techniques commonly used by ransomware as a sample, such as CRC32, derivative loader, and process hollowing. And test with thousands of ransomware as the base, and finally is our tool to allow the blue team to operate in a more convenient way. And first introduction for overview, we know there are many types of malware, and different malware have different behaviors, but they all have different effects on the system. But recently, this year, we have noticed that ransomware has a huge impact on various verticals. So we want to help our defense party, all blue teams, strengthen layer defense against the ransomware. We also have noticed and detected that many emerging ransomware groups are taking off, such as Luckily County, and the propagation of attacks at different time points has gradually increased. Of course, WannaCry is still the highest in our observation, but the propagation has gradually decreased. And also for those complicated ransomware, we prepare the comparison for those different ransomware. We would like to know what kinds of behavior in different ransomware. So as you can see, different ransomware may encrypt, have language check, kill process, persistence, privilege escalation, anti-recovery, and other behaviors. And also, such as Revel or Luckily 2.0, they are very complicated and encrypt almost all techniques in the ransomware. But we know that for the ransomware, the key point is they all of them have partial encryption or full encryptions, and we can base this to detect the ransomware behavior. And seeing the previous ransomware is so complicated, and how is it detected in practice? Traditional signature basis to byte sequence, list of DLL, assembly instruction, and behavior based of heuristic basis to the API code, system code, control flow graph, or the most discussed learning base for API code. There are many ways of behaviors, such as the behavior sequence of system code, but they are all face different problems. And what limitation or problems will be encountered? For example, signature base will require a very large signature database, and it is difficult to defeat obfuscated samples. Well, and behavior base often hide a risk of dynamic execution being bypassed, and it also takes a lot of time to scan. And the code base also needs to connect to the internet in real time. Even the recently popular learning base will encounter the problem of unable to detect the variance due to the limitation of learning samples. So there are different problems, for difficult problems for malware and detection. So to solve whether it is static or dynamic analysis, dynamic time-consuming scanning, the need to update signature, the inability to identify variant and obfuscated samples, and other incredible problems are the point we want to solve at one time. And we also try to not only judge as malicious, more insight in the binary we want to detect it. So let us share our method and build our detection engine through the concept of symbolic execution. First, in our approach, there are 3 previous studies that inspired us. Many thanks for their contribution, and they provide many ideas to build our and complete our research. So first, in 2005, is a lightweight malware template based on data reference relationship was proposed, and which was very normal concept at that time. But unfortunately, the research did not release any tool that can be used for routine. And the concept proposed at that kind cannot be used to solve the problem of obfuscated sample and malware. After that, the study in 2018, the researcher used the hidden Markov model to identify the problem of obfuscated samples. But it is if there are too few parameters, it cannot be an analysis and not all API parameters have match number used as a feature. So there are still some limitation for this research. And the last one is in 2019 is SM2Vect. It's a learning instruction label semantic through the neutral network approach, which can detect the variant samples at a semantic level. But unfortunately, this method lacks the ability to explain why it is recognized as a variant, and this research more suitable for the classification. Based on those wisdom and those research, we are also summarized our method based on malware analysis engine of symbolic execution, is semantic based, and through the recognition of instruction label semantic and the concatenation of various modules, we can effectively identify the technique content in malware binary. So what is symbolic execution and why we choose this? And symbolic execution is a program analysis technology in the field of computer science. By using abstract symbols instead of exact values as a program info variable, and the abstract output result of each path are obtained. And the program you can see it be executed through the symbols. So here we can see the each large gate path is interrogated and set to the constraint for the analysis through the symbols. But we know the symbolic execution is very powerful, but for malware, the basic malicious behavior is mostly abuse the API. So we just focus on the process of data reference from main function to wing SQ function and its parameters. So the relationship between API and parameters, we can use the instruction label based semantic heuristic help us evaluate various behaviors. It's very useful, and we will introduce later. And when we use symbolic execution, we focus on use lightweight part, diffuse relationship, and that is a resolution of association between perimeter functions, and which is enough to solve the problem of malware analysis. And the risk of full static analysis is low, and there is no risk of being bypassed by malleability. And based on the semantic analysis, false positive are very, very low. So the all of them or feasible, they are very feasible we can use, and that's why we choose symbolic execution. And for our engine, for our practical symbolic engines, there are 5 modules and I connect to in series to provide function. The control focus module is responsible for parsing out each control code block. The intent analysis module is responsible for connecting the relationship of each parameter and functions. And the obfuscated API identified is responsible for what it is the function of identify obfuscated sample functions. And our modules is responsible for simulation and the compiler, the compiler space. So through such those engines, we will write extract the symbolic semantic signature as a rule and input it into the engine together with the target to be scanned. The result can be obtained in a very short time, and not only to determine whether it is malicious, but also we can describe what kinds of malicious behavior in the binary, in this binary scan, scanning the binary based on the rules. And then we can have a few seconds, from few seconds to 1 minutes, and we can get the result. It's very quickly and static and stable. And the more in detail information about each module and our experiment, I will hand over to my colleague Senhao in person will present it.
In our symbolic engine, we have designed control flow graph analyze engine can be used to pass a given function into code blocks and analyze each assembly instruction one by one in code blocks. Also, another design is tensor analyzing. And tensor analyzing is actually our engine is designed to fully statically to analyze the PE module. So each function call will not be implemented. Instead, will give a unique value as a return value of each function. And although tensor analyzing is very powerful, but actually a lot of wild sample are actually is fully stripped symbol and do not have any API name inside the binary. So we need to conquer the problem that binary do not have any API and function name inside the binary. So we would like to deal with this kind of problem with the success of NDS's paper. It's possible to infer the original API name. And so if we meet a unnamed API here, and we can dump in our engine, we will dump the unnamed API, and which can be used to recognize the original API names. And here, at first, we created a simple prototype used to statically analyze the prototype, statically analyze the program file, and check each parameter of each function. And we can do a lot of interesting experiments. For example, if we check, the first parameter looks like the generic read, generic write, and the third parameter looks like create OS or open exit. And we can say the syntax matches the form of the created file, right? So we can say, it's probably is a binary instruction, it's maybe a created file here. And here, so we use this prototype to scan all the fresh sample on the ransomware sample on the VirusTotal, and we see a lot of interesting cases, and we took one of these is REvil. REvil is a very famous, very popular ransomware, and fully obfuscated and do not have any API name inside the binary. And here, as we know, REvil actually have a function table to record all the API init inside the binary. Only after dynamically running, you will see which Windows API is inside that pointer. And here's an example here. You can see the pointer is at the 412714. The pointer, we really don't know which API is inside the pointer, right? But here, our engine, without running the sample, it can detect, this sample is just the created file API here because based on the parameter on the stack. And we also use the IDAPRO to double check the same point is the same function point. The same function pointer is that created file or not. So here you can see on the result, IDAPRO result, you can say, this pointer is the return value of this point is got used on the close handle. So we can say, this API just the created file, right? So on the result there, we list on the picture, and you can see our prototype can recognize all the function that looks like created file inside the binary. And with the success of our experiment, we would like to make this cool idea into a powerful analyze engine to help researchers to deal with this kind of hard-to-solve obfuscation malware in the wild. And our engine, TISA TX1 code semantic analyzer, which built in the ViviSat as a decompiler engine. And any researcher can give our engine a program file, and the engine will pass each function of this binary in the binary and analyze each assembly instruction one by one of each function. And at the same time, your rule, the callback function of your will receive an event content, the memory state and address assembly instruction at the same time. So actually, your rule can notate those suspicious API or memory state or stake or any suspicious behavior just in your rule to the following tracing. So here's an easy sample here. Here you can see we write a very, very simple callback function here, only print out the assembly instruction during parsing. And also if the instruction have the API name, that is a function call here, and this instruction have the function name, and we can print out the function name also here. So on the result, you can see here, we can say, oh, this program file try to use the Win API, Win execute API to run some kind of exe file. Or another, besides that, we can say the rule can also get the parameter data of each function code. So there's a sample here. You can say, oh, this program file try to use the create process, this API to run some kind of executable file like CMD. This program try to use create file and create a new CMD file here. But before this behavior, you can see this program file try to use the WSA connect to the remote port 444. So based on the code relationship, we can say, oh, this program file have the ability to do the reverse shell. So here, but still actually, although our engine is pure statically, but still a lot of API is necessary to be implemented, or the program will not be run as a process properly. For example, like as we know, like long library A, get process address, and get full path name. Those API is necessary to run as a process, right? So we in a TISA environment, we do the necessary implementing the necessary API inside our environment. And here, so everybody here can write our TISA rule, and each TISA rule have this three callback function: is callback, initialize, and clean up. And in your rule can do the necessary prepare in the initialize, and also your rule can receive event about read assembly instruction one by one of each function. Also, so your rule actually can notate those suspicious behavior, all the possible behavior of each function in the instruction level. And after TISA engine analyze all the function, and the callback function, the clean up function of your rule will receive an event. And at the same time, the engine will send a message about Yara rule and the Kappa rule second result. So your rule can make the final decision about this program. So here we would like to show a lot of demo here, just multiple demo about CRC hashing, DL reflected loader, and process hollowing, and the ransomware encryptor. And those attacks is very widely used, very popular one, and very widely used by the threat actor. So we would like to, especially we would like to explain how to use our TISA engine to detect them. So here start from a very basic example here, like CRC hashing. And as we know, if you give a read of data to a CRC hash function, and you will receive, actually the CRC hash function will take out the data from the array one by one, and do the XOR behavior with the magic number EBD. So to do the magic number, do XOR for 8 times. So if our rule can see, oh, there's an instruction in the binary try to use the magic number EBD to do XOR for some kind of data for 8 times. So we can make sure, oh, this definitely is a CRC hashing behavior right there. So here's a sample here on the result. You can see, oh, the TISA engine detects there's a CRC hashing behavior just right at the the function at 43 CBD, and on the result of IDA-Pro, you can see here is really a CRC calculation here. But just we know that CRC hashing is quite very simple, right? It's very simple and obvious to detect. So we would like to introduce another one. Is more complex. Is reflected loader. Attacker usually use reflected loader to inject DLL as a shellcode into a remote process. And this trick to hide process, so to hide the malware itself. So also, reflected loader is highly mutated and very tricky for the typical pattern scan. And here is a three-step design of the reflected loader. First is it will try to pass the size of image of its optional header in its memory to make sure how many space need to be allocated to store the whole malware binary into the memory. Also, the second step is to pass the data dictionary of its optional header to make sure to fix up the pointer table for the malware to get the function pointer address. And the final step is to pass the address of entry point of its optional header to locate the entry function of the malware to waking up the malware binary. So once done that design, and that is a reflected loader here, just three-step design. And here, once we know the design of a reflected loader, so we can write a TSAR engine rule, TSAR rule, to detect there's a reflected loader behavior in this kind of in a binary or not. So for example, here we can say, oh, if we detect some kind of instruction, there's an instruction there just trying to compare some kind of data with the magic number PE or MZ. We can say, oh, let's definitely try to locate the emerging NTS header structure inside its memory. So we can put this suspicious structure into a watch list, and if in the following code, if any following code try to use the suspended low suspicious code in the watch list, like such as using virtual locate with the size of the image in the watch list, and we can say, oh, it tried to mount some kind of malware binary into the memory, or it tried to pass the imported dictionary in the watch list, and we can say it tried to fix up its the malware's importer address table, or it tried to pass the address of entry point. We can say, oh, it tried to waking up to locate the entry function to waking up the malware binary. So once our rule detect all the three behavior at the same time in a function, and we can say, oh, it's just a reflected loader here. And here we choose a fresh sample on the just on the July, and it's on the VirusTotal sample here. At that moment, only 8 vendors consider that is a malware sample here. But our engine at that moment can detect, oh, this is very exactly which function have the ability to do the reflected loader. So based on the TSAR rule, we can effectively to solve this kind of problem. Those highly mutated malware that is difficult to solve by the pattern scan. And we are going to introduce another one, is more complex, is process hollowing. And another typical technique used by the malware to hide itself is process hollowing. This practical technique is widely used by the threat actor. So therefore, MITRE has collected with the number T1055. And also, attacker usually use this kind of attack, hollowing attack, to run a malware binary inside a benign process. So that is very difficult for victim to notice they are really under attacker's control. And usually, these hollowing samples are widely are fully obfuscated and fully stripped symbols. So we are going one step further to explain how we use TSAR engine to detect this kind of problem of the obfuscation malware. So here's a three more steps of the process hollowing. The first step is attacker will create a process to run a process in a suspended mode, and using the get thread context to locate the PB structure of the new process. Then once attacker get just get the PEB structure address, then attacker can modify the emoji base of the PEB structure to switching the main exe module to control the exe module. So here, after it decided after download behavior, an attacker can control the main exe. So here, once the B9 process is waking up, and he will run a malware binary instead of the original program file. So once we know how the process hollowing design, as we mentioned, the first step of the process hollowing is using create process to create a new suspended process, right? So our rule can have a watch list of all the API code looks like create process. Then after TSAR engine analyze all the function, and actually we can check those suspicious API things like looks like create process. And here, TSAR rule, our TSAR engine provides an API tiny simulator singulation function. This API is able to let us create a new tiny simulator to run from a specific address and fully simulate the rest of the code. And also provide another API is a lookup caller to locate the entry function of any function based on the control flow graph. And here, when those simulators are running, and actually they will execute the copy function we assign to them, so we can detect there's any kind of sensitive behavior in the rest of the code, just in the copy function. So here we can do tend to analyze the thread and the process value with the dead and the beef magic number. And during the simulation, we can check if there's any code in the following code there's any code try to use get thread context or write process memory to switching to modify the emoji base of the PEB structure, so we can make sure that is definitely is try to do process hollowing because he is trying to control the main exe module. So here in our experiment, we collect all the fresh sample in this year, and they are totally labeled as injection behavior. And we are really curious about how many of them are actually really typical process hollowing behavior. So in totally, we collect 233 sample here, and up to 61% of them are actually a typical process hollowing behavior. And the rest of them, after we do the reversing engineering, we found, that is actually a hacker tool or reversing engineer tool or installation package. And now my colleague Hank will go to the next part. Is more complex one, is how to use TSAR engine to detect ransomware encrypted. And
okay, thanks for the St. Thomas presentation. And hello everyone, I'm Hank. I'm going to talk about how our tool TSAR detects ransomware. In order to successfully detect ransomware, we set up a criteria for ransomware detection, and we must understand the 3 common characteristics of ransomware. And because our criteria is based on these 3 common characteristics. They are file enumeration, file operation, and file encryption. First, these 3 things happen in sequence. So first, ransomware enumerates multiple files on disks, and then file operation is triggered, which means file handle is created for each file, and the file content for each file is also read and written. And finally, each file content is encrypted by ransomware. And to ensure our detection is accurately detect this ransomware, so we also implement the function chain to help us to filter out the detected characteristic not belonging to the ransomware. And there are 2 function chains we try to detect. The first one is file enumeration to file encryption. And the next one is file enumeration along with file operation to file encryption. So now you understand how our criteria, and I would like to show you the implementation of the rule of these 3 common characteristics. So here is the first one, file enumeration. in file enumeration, we try to identify the strip find first file and find next file. And then we compare the return value from the find first file and the first argument of the find next file. And then we can analyze the file name usage, so we can easily record the file name usage in our detection log. So when maybe you can see the log to analyze how the ransomware works. And so after we understand the first characteristic of our tool, I would like to show you the next one is file operation. And for the file operation, we try to identify the strip create files and other API related to the file operations. And then analyze the file handle returned by a create file. To help you understanding how the rule works, I would like to show you the detection process in more detail. For example, our tool analyze the file operation, which store the file handle in the local variable, and which is in the stake. And then it is expected that each file operation load the file handle from the local variable. The instruction highlight with the red box shows that we can successfully detect the characteristic of file operation in Babuk ransomware. And for the third characteristic, file encryption, we adopt the hybrid strategy consisting of obfuscating identification rule and the pattern-based rule. And for the obfuscating identification rule, which is for identify the strip cryptography function of Windows API. And the pattern-based rule is for identify the multiple complex encryption algorithm. So this is the rule for the 3 common characteristics in our tool. And I would like to show you how our detection log is. And to verify our tool is work, we can review this detection log. And we bring 3 different ransomware and verify their log. And you will see the 3 common characteristics in each detection log. And the first one is Babuk ransomware. You can see the file enumeration is detected, and we can compare it with the snapshot from the IDAPRO. And there's also have made multiple potential enumeration files usage in our detection log. And then in the file operation, we also record some file handle usage from our tool. And you can also review this log to verify where is the real file operation. And then in the file encryption, you can also do the same things. And this is the whole process, and you can follow this step to review. We can actually detect the ransomware. And so the following, we have another ransomware is called DarkSide, and because they are in the same process, so I will go through this very quickly. And in DarkSide, we can easily detect the file enumeration and file operation and file encryption. And then as for LogB, we can do the same things because we didn't have much time to share this about. Okay, so in LogB, we can also detect the file enumeration, file operation, and file encryption. And I would like to show you how we improve our detection rate because there's lots of encryption algorithm in the real world, and which is not easy to implement this pattern-based rule. And for DarkSide, it utilizes the customized CELSA 20, which has a customized matrix, and we can detect it because it is not in our existing detection rule. So we capture the feature from the DarkSide, and we implement the pattern-based rule to detect it. And another example is about 7 ransomware. There's 2 things about 7 ransomware. And first one is R5A encryption. And this encryption is also not in our existing rule, so we just implement the pattern-based rule to detect it. And another one is FS Open, because just as I mentioned earlier, we focus on the create files, but the 7 ransomware use FS Open instead of create files. So we just implement a pattern-based rule to identify the byte sequence of FS Open so we can detect this one. And we also did a large-scale experiment. For the whole year, we collected ransomware samples, which labeled as a ransomware by 3 different popular antivirus vendors in the VirusTotal. And there's one thing you need to know. In the VirusTotal, the sample labels as ransomware now means it will encrypt files. This is very surprising. And so we also use the commercial sandbox to filter out some samples, and it was really encrypting files. So we can collect them for our final sample set. And finally, we have an impressive detection rate around 96%. And so here's the table about the ransomware family we can detect. There's 64 ransomware family we can detect. And we also can detect its variants in these families. And however, there is still some undetected samples in our experiments. For example, PwnDarker, it used an unknown encryption algorithm, which is not identified before. And so, just like before we did for the dark side, we can just implement a pattern-based rule to capture some feature in this encryption algorithm to implement the pattern-based rule to identify this one. And we also wonder, does our tool mistaken other malware as a ransomware? So we did false positive experiments and find out, finally we have a false positive around 0%, and which shows that our tool can really accurately detect ransomware. And so now I would like to Senghao Ma will summarize our presentation.
Okay, thank you, Hank. And the final part is future work and a takeout point. And here's a 4 takeout point. First, we realized in this session that existing detection techniques have their strength and the limitation. It's difficult to perfectly solve the highly mutated ransomware in the world. And second point, we use symbolic execution to detect those multiple malicious attacks and show the good result, which is difficult to achieve with the pattern scan-based malware detection. The third point is our experiments show that such as a lightweight symbolic solution can solve real-world sample and it's robust against obfuscation. The last point is we hoped this engine can help the blue team in the world, so we release it on the GitHub and hope the community can join us to write TISA rule to enhance the diversity of the detection capability. So as we mentioned, here is a QR code to our TISA engine on the GitHub. We hope there are more and more researchers to join us to working on this engine. So thank you for listening. We are TX1. If you have any question, please feel free to ask your question or contact us by the Twitter or LinkedIn. And thank you, everyone.